hardware. Mario Bergeron from Avnet. Mario is a technical marketing engineer for Avnet Electronics, marketing, specializing in video, image, and digital signal processing. Mario has a Bachelor's of Science degree in computer engineering from University of Laval in Quebec City. He started his career as an ASIC designer and has since accumulated more than 10 years worth of DSP and FPGA-based design experience. His present activities include co-processing and video development platforms, reference designs, and customer training. Mario, I'll turn it over to you.
All right, so test 1, 2. The wireless mic. Thanks Brian. Thanks to the Embedded Vision Alliance for allowing me to make this presentation, which is targeting computer vision algorithms to embedded hardware. My name is Mario Bergeron. I work for Avnet Electronics Marketing, as Brian pointed out. Who is Avnet? Avnet is a global distributor of electronic components, serving over 80 countries. So basically what we do is connect over 100,000 customers to leading technology manufacturers. And the value add that Avnet brings is we try to showcase technology from different manufacturers together as system solutions whenever we can. And we do this in the form of electronic boards, development kits, reference designs, and live or online trainings. So obviously the fact that the Embedded Vision Summit is even happening is a testimony to the fact that embedded vision is growing at a tremendous pace for various reasons, right? I think this involves two main components. Obviously, the computer vision algorithms, which are usually available as algorithms. And also, if you're making a product, embedded product, we're talking about hardware architectures, right? Which are starting to be created by manufacturers that are optimized for embedded vision. So that's really good news if you're making a product. The motivation for my presentation is I wanted to address what are the implications of turning a computer vision prototype into a product, specifically on embedded hardware, just from a global perspective, just to get insight on why manufacturers are making these optimized hardware architectures for embedded vision. And also, what would an engineer need to know to choose the embedded vision application, the embedded vision platform that's ideal for their products. So this is a quick overview of my presentation. I'm going to touch on just defining what embedded vision is and overall different types of image and processing, video processing algorithms that are out there. Then I'm going to create a theoretical pixel processing system. We'll define its requirements, look at the challenges of moving that system to an embedded implementation, and finally see how we can optimize this system to be more efficient. And then I'll move from the theoretical to the practical and just highlight two examples that manufacturers are making that just reinforce the points that I've covered of how these optimized architectures are actually needed for embedded vision applications. So what is embedded vision? As other presentations have already covered, it's computer vision on embedded hardware. So the first aspect, computer vision, this is usually in the form of toolboxes. This may be proprietary, or you may be already making image or video processing algorithms yourself. This may be commercial. There is toolboxes and tool suites, complete tool suites that you can buy that really increase your productivity. One example is the computer vision system toolbox from the MathWorks. It could be open source. There's a lot of talk today about OpenCV, open computer vision. The main goal of some or most of these toolboxes is, first off, algorithm exploration, right? It's to create an application, a prototype. They're not necessarily meant to go to target hardware or the hardware that you have chosen. So the other end to this is, obviously, if you're making a product, this computer vision application that you've built has to run on embedded hardware. So this can either be a general purpose embedded hardware, depending on the bandwidth you're talking about, or you may need to go to specialized hardware, especially for the higher resolution and frame rates. So, and obviously, embedded hardware, the main goal will be a real-time execution, and most probably low cost and low power. So there's a lot of different types of image and video processing algorithms out there, which I'll roughly categorize in terms of data rates and complexity. The first category, which are the simplest in the complexity scale, but the very compute intensive, are what we'll call the pixel processing algorithms. These ones take an input image, modify it in some way, maybe do color space correction, remove noise. So they're basically cleaning up and enhancing that image, and they produce an image at its output. The next category may be feature detection, where this one takes an image as an input, but will create metadata at the output. So the data rates will start to come down in the video pipeline. Examples of this may be just generally regions of interest, corners, lines, colors, textures, right? We're looking for features, it's the foundation of starting to understand what's going on in the image. And then this moves up in the complexity scale where algorithms will start to recognize objects and possibly track them in the scene. And these are quite complex, but usually tend to work on smaller data sets, smaller data rates. So this is a simplistic view of the landscape of algorithms, but this is what I'll be working with. An embedded vision application will typically be implemented on both hardware and software. So there's no magical delimiter that you can follow that'll tell you where this hardware-software partition occurs. But if you've searched the internet, you'll notice that the simplest, very compute-intensive pixel processing algorithms are the first to be considered for hardware implementations. You'll also find some feature detectors that are detection algorithms that are being implemented on hardware. And then finally, the more complex algorithms that are recognizing and tracking objects are usually, since they're working at smaller data rates, having implementations in software are usually the most efficient way to go. So this presentation has a focus on hardware. So I'm going to be concentrating on this first class of algorithms, the pixel processing algorithms. So the example that I looked at, I went on the Embedded Vision Alliance website, and Eric Grigori created a great example describing the candy edge detection algorithm, which is a very popular algorithm. So I'm kind of building up on that one. And this algorithm is composed of different components. I will not cover all of them, but there's basically a few filtering operations that occur at the start of the candy edge detection algorithm. It starts by just cleaning up noise with a Gaussian smoothing filter. Then there's two Sobel edge detectors for detecting edges on the vertical and horizontal. And then these are combined together to create a vector which has magnitude and an angle. And from there, based on the angle, they can get rid of the data that's not at the maximum edge. And then there's additionally some hysteresis that'll clean that up so you can get a nice fine line at the output. As it turns out, the most compute-intensive parts of this algorithm are these three filtering operations. So I'm just going to describe those. If we take this image, right, it's a grayscale image. You'll notice there's a lot of dots. The dots here represent noise, unwanted noise, salt and pepper noise. I've exaggerated it so we can see it. But there's also lines that are that information that we want to find. So both of these features are characteristic of high frequency content, right? The dots come out as high frequency, and the edges also come out as high frequency content. So what the candy edge detection algorithm does, it starts by removing the unwanted high frequency content. And this is done with the Gaussian smoothing filter. So if we send that out, we get rid of our noise. And then the next step is we apply these edge detectors, which will then keep the high frequency content and preserve the edges. So that's kind of what it looks like. And then there's the additional steps. But right now, for the rest of my presentation, I'm going to be looking at these three first functions, because as they turn out, they're all two-dimensional convolution filters. So that's the example I'm going to run with here in this example that we're going to build. And you'll see, even with this very simple example, on very high video resolution, the numbers quickly get out of hand when you're moving this to an embedded system. So let's build a simple example to illustrate the point. I'm going to use a high-definition image sensor with 1080p resolution, running at 60 frames per second. The reason I've chosen 1080p 60, I'm not telling you that you need to put 1080p 60 in your embedded vision application. It's more, I want just people to realize it's not just a marketing buzzword that you want to put on your product. If you can get by with smaller resolution, that is definitely the way to go. If you do need 1080p 60 maybe for higher end application, industrial applications, then you just need to know that that's a lot of bandwidth in your system. And we're actually going to walk through this just to get an insight on exactly how much bandwidth we're talking about. On the output, we'll simply send this out to an HDMI monitor at the same resolution, 1080p at 60 frames per second. And in the middle, as I mentioned, the processing that we'll implement is a 2D filter, two-dimensional convolution filter. And to start off, we'll assume that we'll implement this with a general processor. So modern processors or DSPs have typically multiple cores, internal memory, as well as various peripherals. So the first thing to consider is video storage. Usually in a video system, you don't want to be processing a video frame that's being received. So you'll need the intermediate storage of these video frames before processing them and sending them out to the output. So how much storage do we need? Well, for 1080p 60 resolution, that's 1920 by 1080 pixels. If we assume 16 bits per pixel, that would be 33 megabits. So first challenge that we're faced with, modern processors will usually have a few megabits of internal memory inside. So we can't store these video frames inside the internal memory of these devices. For high definition video, we have to go to external memory. And that's usually not a problem because modern processors have DDR-like memory interfaces. So this memory can be shared between the application and the video frame buffer. The next thing to consider is the I/O. How do we get video in and out of our processor? Well, let's look at that resolution that we have. 1080p 60 resolution. We're taking our 33 megabits per frame, multiply that by 60 frames per second, we get 2 gigabits per second, right? And if we were using 32 bits pixels, that'd be 4 gigabits per second, which corresponds to the demo that we have at our table. But if we assume 16 bits, one stream of video would be 2 gigabits per second of bandwidth. So obviously, putting these interfaces on some kind of shared bus is not feasible or realistic. So the first thing, another challenge that we face with is you need to find a processor that has dedicated high-speed video interfaces. Now we move to the processing inside. We mentioned it was a 2D filter, so I'm just going to dive into what that is. So for every pixel that we want to process, we're going to do the same algorithm. So for each pixel, we're going to go get, in external memory, the surrounding 5x5 neighborhood, perform a convolution with an equally sized filter of coefficients, and then write that output result back to external memory. Right? Simple enough. But remember, this algorithm is going to be performed on every single pixel. We're talking about millions of pixels. Right? That's quite a lot of stuff going on. So to recap, for each input pixel, we need to perform 25 memory reads from external memory to get that neighborhood around the pixel. We need to perform 25 multiply accumulate operations to perform the convolution, which is the filter, right? And then one memory write to bring the result back to external memory. So back to our system, at 1080p 60 resolution, what does this mean? Well, our 25 multiply accumulates for each of the 1920 by 1080 pixels at 60 frames per second. We're at over 3 gigamax per second. That's quite a bit of compute operations, and we're just talking about one simple algorithm here. In terms of memory bandwidth, we want to write, we're essentially reading the image 25 times, right? Because for each pixel, we're reading that 5x5 neighborhood. So this turns out to 50 gigabits per second of bandwidth that we need to read, process it, and then we write the result back to the output, which is 2 gigabits per second. Now, the compute part is impressive, but what's really jumping out here is this memory bandwidth. We've obviously quickly gone out of hand with this, and that's a challenge when creating an embedded system because external memory accesses are expensive, not only in terms of performance, but in terms of power consumption, right? Toggling all those pins at these data rates is just going to consume power. You need to avoid that if you can. So already, just with this simple example, we're at 56 gigabits per second of bandwidth to external memory. That's catastrophic. So we need to optimize that. So this is what I'm going to start to do. So the first obvious thing to do, one thing that could have jumped out at you, is to cache the pixels, right? We don't really need to read the image 25 times from external memory. What we want to do is cache the pixels in internal memory, similar to what a processor cache would do. So if we take a pixel in a line, we'll read the entire line, save it in internal memory, and then the next time we need to take a pixel from that line of video, Well, we just grab it from internal memory. So this has gone down drastically, right, just by doing this. One way to achieve this could be by rewriting your code explicitly to implement these delay lines, these video delay lines, into internal memory. Another way could simply be to use the processor's built-in cache mechanism. But one challenge of using that mechanism is the processor cache might not be dedicated to video, so the results will vary. A more deterministic way of caching the pixels would be to use direct memory access, or DMA engines. These hardware resources can be programmed to very efficiently transfer data to internal memory for processing. So the advantage of doing DMA engines is that these will be operating in parallel with the processing. So that'll significantly improve the overall system performance of the system. And while on the subject of DMA engines, these are also usually used in the dedicated high-speed interfaces to move data to external memory or to other peripherals in the system. So now that we've optimized our memory bandwidth to a certain degree here, now I'm going to move to the compute portion of the algorithm, right? Because right now our algorithms are running on a sequential processor. That is not the best place to be doing this type of processing. Remember, we're doing the same algorithm on millions of pixels, right? So let's try to see what we can do to optimize that. Well, when we're talking about computation, we want to accelerate with hardware, dedicated hardware. Most of the modern processors and DSPs have hardware resources that allow you to perform multiple operations simultaneously in parallel. One of these is the SIMD, single instruction multiple data, right, which as the name indicates can perform the same operation on multiple data sets at the same time. So that's a good thing for video, right? So this can be achieved either automatically using compiler switches or explicitly coded by yourself to use that specific hardware resource in the processor. So I've put some benchmarks here that I've researched. On Intel, they published that they're achieving an average of 5x acceleration on the OpenCV library using their SSC SIMD engine. On the ARM, Neon can get you maybe up to 2x with the compiler switch. This I got from the Embedded Vision Alliance. Eric Grigori made the test where he turned the compiler switch on with the face detector and got a 2x improvement on that. So that was interesting. And this other number, this 5x, I've taken from Uncanny Vision, who are making libraries, optimized versions of the OpenCV libraries for the Neon that take advantage of the Neon SIMD engine. So they're getting an average of 5x acceleration with their library. So that's a good example of if you explicitly code this, you can get that optimization. So the challenge of using SIMD engines is that you probably need to do some explicit coding or purchase optimized libraries to achieve that acceleration. And ultimately, there's an upper limit to that acceleration, which is lower than another method of acceleration, which we'll talk about in the next slide. And that is an application-specific accelerator, right? The best hardware accelerator for a given function is hardware that does exactly that function, right? That's the most optimal that we'll get. So in the case of our 2D filter, this would consist of internal memory to implement our pixel cache and implement our filter coefficients. It would also consist of dedicated MAC engines, and many of them, so that we can execute the 25 multiply accumulates in parallel, right? So this would give us a theoretical 25x. It would actually be more because there's a lot of I/O happening when that's being done in the processor. But the theoretical 25x acceleration for a 5x5 2D filter. And if you've got, let's say, 4 of these in the system, or for the canny edge detection, remember we've got 3 of these filters going on in there. So if we have 3 of these accelerators, we've got a 75 times acceleration, right? So if you're a hardware designer, a few things could have jumped out at you here as well. And the fact that the accelerator is decoupled from the video interfaces. This creates unnecessary bandwidth to external memory as well. So that's another thing that should be optimized, right? If we can move the accelerator in line with the video data path with our hardware architecture, well, then we've saved these 4 gigabits per second. And if we do the same thing on the output, right, whenever you can, you try to minimize the external memory bandwidth, because that's going to consume a lot of power. So moving these accelerators, the ability to move these accelerators in line to the video data path removes unnecessary external memory accesses, reduces power consumption, and the overall synchronization of the elements together. So this frees up your processor to do other tasks, maybe more of the complex analytics that you'll see in your video embedded vision application. So the challenge of this, all the theoretical optimizations that we talked about, is ultimately you need to build a hardware platform, right? So if you're in the business of ASICs, that's probably not a problem. You may use something like the Synopsys Embedded Vision Starter Kit to create your own ASIC. But if you're not in the business of ASICs, then you need to create a processor. But the good news is that there's a lot of manufacturers that are creating these hardware architectures that are optimized for vision. So I want to cover two of these examples that kind of reinforce the points that we talked about. The first one is from Analog Devices. It's the BF609 dual-core Blackfin vision processor. Here we have two Blackfin DSP cores. We see our internal memory, our external memory that we're used to seeing. But what's unique here is we have a video subsystem. This video subsystem has dedicated high-speed video interfaces that you could use to interface to image sensors or displays. It has a pixel compositor, which can do some various pixel processing algorithms, such as color space conversion. The most interesting piece in this device is the pipeline vision processor. It can do 4 instances of our 5x5 convolution filter. So here we're talking about 100x acceleration right off the bat. And also, equally important is the very optimized video interconnect. What this allows you to do is place those accelerators in line with the video data path. So for certain algorithms, you won't even need to go to external memory. And that'll save you a lot of bandwidth here for your overall system, but more importantly, reduce power. So this is a very power-conscious device, optimized for vision. The other device that I wanted to illustrate is a device from Xilinx. It's the Xilinx Zinc 7000 all-programmable SoC. And this is essentially 2 ARM cores, right, in this dedicated system here. It has a memory controller and some dedicated peripherals, but it combines with FPGA technology, programmable logic. So what this device does, that programmable logic is basically a clean slate where you can create your own design. So you can create your high-speed video interfaces. You can take pixel processing algorithms from an existing library of IP cores and build that into your system. And in terms of data path, well, this is entirely designed by you. So you can create the most optimized data paths in your system, right? If you need to go to external memory, there's video DMA engines that are there that allow you to do that. But if you can do the whole pipe within the fabric, then you'll be saving bandwidth and power here, right? So moving OpenCV functions to the ARM cores is fairly straightforward, right? We know that OpenCV is supported on ARM. That's no problem. But the challenge with this device would be, how do you move that to the programmable logic? And I don't want to steal the thunder from the next presenter, but there is a tool that the Xilinx provides, which is called high-level synthesis. And the next presenter is going to dive more deeply into this, which allows you to take OpenCV functions, which are in C, and move them to the programmable logic. And that can give you up to 100x acceleration or more. So that's very interesting technology. So, but the next presenter is going to go more into detail into that. So you can put it in line or connect it to the external memory. That's for you to decide. So in conclusion, I hope I convinced you that computer vision needs specialized hardware for real-time execution, especially if you're talking about really high definition video. And the good news, if you're making a product, is that there's a lot of manufacturers creating optimized hardware architectures specifically for embedded vision, so it's a great time to be making products. And what would you need to look for when selecting an embedded vision platform? Well, I touched a few of these items, so I'll just re-mention them. Obviously, you need dedicated high-speed video interfaces. These will usually be associated with DMA engines, so you can efficiently move data into your system. You'll want to have hardware accelerators. Depending on the resolutions you're using, SIMD accelerators might be enough for you, which will get you 2 to 5x acceleration. But you may want application-specific accelerators, which hardware manufacturers are starting to embed into these products, which can get you 10 to 100x or even more acceleration. And obviously, one point not to forget is you need some flexible data paths. And this is important so that you can move your video accelerators into the video data path, which will prevent you from moving to external memory unnecessarily and thus save power. So that was the end of my talk. I don't know how much time I have left. So if you want to investigate these a little more, definitely go to the Embedded Vision Alliance. There's forums. There's a lot of very interesting posts that are being presented there. We have 2 community websites, which are community boards, community development boards, that feature the 2 devices that I touched on in this presentation. And if you want more information on these 2 community boards, come by the Avnet table and we'll show you a demo of each of these community boards.